Article 517.17 of the National Electrical Code addresses ground fault protection in healthcare facilities. It specifically deals with situations where ground fault protection is required at the service disconnecting means, particularly in 480-volt systems rated at 1000 amps or more. The initial statement suggests that all downstream feeder breakers must have ground fault protection, regardless of their amperage rating, in such systems. However, this is not entirely accurate. The code mandates an additional level of ground fault protection only at the first level of feeder disconnecting means downstream from the service equipment if that feeder disconnecting means is rated at 1000 amps or more. It does not require all downstream feeder breakers to have ground fault protection. Only those feeder breakers rated 1000 amps or more and directly downstream from the service disconnecting means are subject to this requirement. Now let's consider the second part of the statement concerning medical office buildings. This statement suggests that this requirement applies to a medical office building containing radiology areas and basic patient care areas, even if it is not a hospital governed by OSHPA regulations but does contain examining rooms and outpatient procedures. This assertion is correct. The requirement for additional ground fault protection applies to all healthcare facilities, including medical office buildings, when the conditions outlined in Article 517.17 are met. The rationale behind this is the inherent risk of electrical shock hazards in any healthcare environment, regardless of the complexity or invasiveness of the procedures performed. Examining rooms and outpatient procedure areas present potential risks related to electrical equipment used for diagnosis, treatment, and monitoring. Therefore, even in facilities that are not full-fledged hospitals, the code recognizes the need for enhanced electrical safety measures. To summarize the application of Article 517.17, firstly, determine if ground fault protection is required at the service disconnecting means. This typically applies to 480-volt systems rated 1000 amps or more. Secondly, if ground fault protection is required at the service disconnecting means, identify the first level of feeder disconnecting means downstream from the service equipment. Thirdly, if any of those first level feeder disconnecting means are rated 1000 amps or more, they must have an additional level of ground fault protection. This does not extend to all downstream feeder breakers, only to those that meet the 1000 amps or more rating at the first level. And fourthly, this requirement applies to all healthcare facilities, including medical office buildings with radiology areas and patient care areas, regardless of whether they are governed by OSHPA regulations. In essence, if a medical office building has a 480-volt system with a service disconnecting means rated 1000 amps or more that requires ground fault protection, then any downstream feeder breaker rated 1000 amps or more at the first tier of distribution must also have ground fault protection. It is important to note that the specific requirements for ground fault protection, including the settings and coordination, are detailed in the National Electrical Code and should be carefully followed to ensure the safety of patients and staff. The purpose of ground fault protection is to detect and interrupt ground faults, which are unintentional electrical connections between a live conductor and ground. These faults can create dangerous touch voltages and pose a significant risk of electrical shock. In healthcare facilities, where patients may be more susceptible to electrical hazards due to their medical condition or the presence of conductive surfaces, ground fault protection is particularly critical. The additional level of ground fault protection required by Article 517.17 provides redundancy and ensures that even if the primary ground fault protection system fails, a backup system is in place to protect against electrical hazards. Let's delve deeper into the technical aspects of ground fault protection. A ground fault occurs when there is an unintended connection between an energized conductor and ground. This can happen due to insulation failure, accidental contact with grounded metal objects, or other unforeseen circumstances. When a ground fault occurs, a large amount of current can flow through the ground path, creating a dangerous voltage potential. Ground fault protection devices are designed to detect this abnormal current flow and quickly interrupt the circuit, preventing electrical shock and minimizing damage to equipment. There are two primary types of ground fault protection systems. Firstly, ground fault circuit interrupters or GFCIs, and secondly, ground fault protection of equipment, or GFP. GFCIs are typically used in branch circuits to protect individuals from electrical shock. They detect very small ground faults, typically in the range of 4 mA to 6 mA, and quickly trip the circuit, interrupting the flow of current. GFP, on the other hand, is used to protect equipment from damage caused by ground faults. It detects larger ground faults, typically in the range of 30 mA to 50 mA, and trips the circuit, preventing damage to equipment and reducing the risk of fire. In the context of Article 517.17, the additional level of ground fault protection typically refers to GFP, as it is intended to protect the electrical system and equipment from damage caused by ground faults. The NEC provides specific guidelines for the selection and installation of ground fault protection devices, including the trip settings, time delays, and coordination requirements. It is crucial to follow these guidelines carefully to ensure that the ground fault protection system functions correctly and provides adequate protection. Coordination of ground fault protection is particularly important in systems with multiple levels of protection. The goal is to ensure that the ground fault protection device closest to the fault trips first, minimizing the disruption to the rest of the electrical system. This requires careful selection of trip settings and time delays for each ground fault protection device. In the case of Article 517.17, the additional level of ground fault protection should be coordinated with the ground fault protection at the service disconnecting means to ensure that the feeder breaker trips before the service breaker in the event of a ground fault in the feeder circuit. This prevents a complete shutdown of the electrical system and minimizes the impact on critical healthcare functions. Let's consider a practical example to illustrate the application of Article 517.17. Imagine a medical office building with a 480-volt service rated at 1200 amps. The service disconnecting means is equipped with ground fault protection. Downstream from the service disconnecting means there are two feeder breakers, firstly a 1000 amps feeder breaker supplying a large radiology suite, and secondly a 600 amps feeder breaker supplying general office areas. According to Article 517.17, the 1000 amps feeder breaker supplying the radiology suite must also have ground fault protection. This is because it is a first-level feeder disconnecting means downstream from the service equipment, and it is rated at 1000 amps or more. The 600 amps feeder breaker supplying the general office areas does not require ground fault protection under Article 517.17, as it is rated below the 1000 amps threshold. However, it may still be required to have ground fault protection based on other sections of the NEC or local codes. The ground fault protection and the 1000 amps feeder breaker should be coordinated with the ground fault protection at the service disconnecting means to ensure selective tripping. This means that the feeder breaker should trip before the service breaker in the event of a ground fault in the radiology suite feeder circuit. In addition to the requirements of Article 517.17, healthcare facilities must also comply with other electrical safety requirements in the NEC, such as those related to essential electrical systems, isolated power systems, and equipotential grounding. Essential electrical systems are designed to provide backup power to critical healthcare functions in the event of a power outage. These systems typically include generators, automatic transfer switches, and distribution panels that are specifically designed to support life safety and patient care equipment. Isolated power systems are used in critical care areas, such as operating rooms and intensive care units, to minimize the risk of electrical shock to patients. These systems use isolation transformers to isolate the electrical supply from ground, preventing ground faults from creating dangerous touch voltages. Equipotential grounding is a technique used to minimize voltage differences between conductive surfaces in patient care areas. This helps to reduce the risk of electrical shock by ensuring that all conductive surfaces are at the same potential. In summary, Article 517.17 of the NEC requires an additional level of ground fault protection at the first level of feeder disconnecting means downstream from the service equipment if the service disconnecting means requires ground fault protection and the feeder disconnecting means is rated 1000 amps or more. This requirement applies to all healthcare facilities, including medical office buildings, and is intended to enhance electrical safety and protect patients and staff from electrical hazards. It is important to consult the NEC and local codes for specific requirements and to ensure that the ground fault protection system is properly designed, installed, and coordinated. Furthermore, regular testing and maintenance of ground fault protection systems are essential to ensure their continued effectiveness. Ground fault protection devices should be tested periodically to verify that they are functioning correctly and that the trip settings are appropriate. Maintenance should include inspection of wiring connections, cleaning of components, and replacement of any damaged or worn parts. By adhering to these guidelines and implementing a comprehensive electrical safety program, healthcare facilities can minimize the risk of electrical hazards and provide a safe environment for patients and staff. It's also worth noting that the interpretation and application of the NEC can sometimes be complex and may vary depending on the jurisdiction. Therefore, it is always advisable to consult with a qualified electrical engineer or inspector to ensure compliance with all applicable codes and standards. They can provide expert guidance on the design, installation, and maintenance of electrical systems in healthcare facilities and help to ensure that they meet the highest standards of safety and reliability. The National Fire Protection Association, or NFPA, which publishes the NEC, also offers resources and training programs to help electrical professionals stay up to date on the latest code requirements and best practices. These resources can be invaluable for ensuring compliance and promoting electrical safety in healthcare facilities. Finally, remember that electrical safety is a shared responsibility. Everyone in a healthcare facility, from administrators to maintenance staff, should be aware of the potential electrical hazards and take steps to minimize the risks. This includes following safe work practices, reporting any electrical problems promptly, and participating in electrical safety training programs. By working together, we can create a safer environment for patients, staff, and visitors in healthcare facilities. In addition to the technical aspects of ground fault protection, it is also important to consider the human factors involved in electrical safety. Human error is a significant cause of electrical accidents, so it is crucial to implement procedures and training programs that minimize the risk of human error. This includes providing clear and concise instructions for operating electrical equipment, ensuring that qualified personnel perform maintenance and repairs, and promoting a culture of safety awareness. Furthermore, it is important to consider the needs of vulnerable populations, such as patients with medical conditions or disabilities. These individuals may be more susceptible to electrical hazards, so it is essential to take extra precautions to protect them. This may include providing additional training for staff who work with vulnerable patients, using specialized electrical equipment designed for healthcare environments, and implementing additional safety measures in patient care areas. By addressing both the technical and human factors involved in electrical safety, healthcare facilities can create a safer and more reliable electrical system that protects patients, staff, and visitors from electrical hazards. Continuous improvement is key to maintaining a safe electrical environment. Healthcare facilities should regularly review their electrical safety program, identify areas for improvement, and implement changes to enhance safety and reliability. This may include updating electrical codes, implementing new technologies, and providing ongoing training for staff. By embracing a culture of continuous improvement, healthcare facilities can ensure that their electrical systems remain safe and reliable for years to come. And just to reiterate, the 1000 amps rating is a critical threshold. If the feeder is rated below 1000 amps, even if ground fault protection is present at the service, the additional layer isn't mandated by this specific section for the feeder. The focus on healthcare settings underscores the heightened sensitivity and potential risks associated with electrical systems in these environments.